And this video is on intermolecular forces and a quick overview of the three states of matter. Okay, so there's a chart on your note paper. We're working off of our note paper that looks like this. And your chart at the top has a comparison of a gas, a liquid, and a solid. So super quickly, all things that you know, but worth mentioning again. The gases take the shape and the volume of the container that they're in, meaning they will expand to fill any size container. They are compressible because there is a lot of space between the particles, and that space can be eliminated by compressing the gas or decreasing the volume. And gases diffuse quickly. If you can remember diffusion, where a gas spreads out from high concentration to low concentration, you can think of like spraying a perfume. That's diffusion. In contrast, liquids take only the shape of their container. If you think about a glass of water, right, the water takes the shape of the glass that it's in, but doesn't necessarily fill it. Okay, it doesn't expand its volume to fill it. They flow readily. They're often referred to as fluids because they flow, and they're incompressible. Okay, so you really can't take a liquid and compress it any further. Solids retain their own shape and volume. They don't take the shape or the volume of any container you put them in. They're also incompressible. Okay, you can't decrease the space between their particles. So that's all old information, but the kind of the takeaway point here is that the state of matter of a substance depends on the strength of its intermolecular forces. So the fact that, let me think of something. The fact that, it just escapes me at the moment. Okay, the fact that fluorine is a gas, F2, at room temperature, chlorine's a gas at room temperature, bromine's a liquid at room temperature, and iodine's a solid at room temperature. Okay, that depends on the intermolecular forces, which is the discussion of today's video. Okay, so first we're going to do what intermolecular forces are, and then we're going to go through the specific types of them. Intermolecular forces are often referred to as IFs. For short. It gets kind of time consuming to write intermolecular forces over and over again. And so the I for intermolecular and the F for forces. Okay, so I'll use IFs a lot as an abbreviation. Okay, so first of all, we need to differentiate between intermolecular forces and intra. So I know you don't have a whole lot of space, but we'll squeeze this in. So we're first going to do intramolecular. Okay, so it's an A. So if you want to think intra with the A, think atoms. An intramolecular force is the force that holds atoms together within a molecule. Okay, so we are talking about two types of intramolecular forces that we always talk about in chemistry, and those are ionic bonds and covalent bonds, okay? So if you think about, water. Okay, if we're talking intra, we're talking about the force that holds this O to the H and the force that holds this O to the H, okay? And that's a covalent bond. So intra, you pretty much have two choices. They are ionic or they're covalent. Okay, we know for the most part that ionic bonds are stronger than covalent bonds, but intramolecular forces are both very strong. Now we have inter. Okay, so intermolecular force is not the force that holds atoms together, but it's the force that holds molecules together. And there are several different types. So basically, if we're talking about a glass of water, I'm not going to draw its structure, okay? But if we're talking intramolecular, we're talking what holds the H and the O together, a covalent bond. If we're talking intermolecular, we're talking what is the attractive force that brings the water molecules together, okay? That's an intra Oh my gosh, I'm sorry. That's an intermolecular force. And we're going to learn today about several kinds. Their names are things like ion dipole, dipole-dipole, dispersion forces, and hydrogen bonding. Okay, there are 4 main types of intermolecular forces. So it's a big point. It's a huge point in this chapter. Okay, the difference between inter and intra. All right. Another point to notice is that boiling points and melting points are going to be related to intermolecular forces. States of matter are related to intermolecular forces. Okay, so we'll tie that all together here shortly. Okay, so the first one is called ion dipole. And you might be, you might suspect that an ion dipole intermolecular force deals with an ion and something that has a dipole. Okay, so it exists between an ion and a partial charge on a polar molecule. Okay, so ion dipole forces exist between an ion and a partial charge on a polar molecule. Remember that partial charge can be considered a dipole, and that's where that's going to come into play. So this is most important for ionic substances in polar liquids. I'll just say things. Which our favorite polar liquid in chem is H2O. Okay, so the way this works is if we, so our I'm not saying it's the only one, okay, but H2O is the one that's going to often happen here in ion dipole. If we think about H2O and its structure, it looks something like this. It's bent, right? Notice I'm drawing it geometrically correct. It has partial charges, and the whole molecule is polar because those dipoles don't cancel. So your O is partially negative, more electronegative, and your H's are partially positive. Okay, all old information. So from here, we talk about if we put an ionic substance in water, let's say NaCl. Okay. Oh, we know that NaCl is going to ionize, and it doesn't exist as NaCl. It exists as Na+, and Cl-. And so there's going to be a huge attractive force when you put an Na+ up close to the partial negative of the oxygen. So the sodium's positive charge and the partial negative of the oxygen, that's a huge force of attraction. And the same thing can be said for when you put a chlorine with its negative sign up near the partial positive of a hydrogen. Okay, huge attractive forces, and that attractive force is called an ion dipole attractive force, or intermolecular force, I guess I should say. Okay, so that's your first intermolecular force, ion dipole. It's basically only going to be when ionic things are dissolved in water. Okay, so ionic substances in water, ion dipole. There's a question that says, in which of the following mixtures do you encounter ion dipole forces? CH3OH in water or calcium nitrate in water? It's a pretty easy question if you think about it. The definition of this says ionic substances because they're going to ionize. So your answer is the calcium nitrate. Okay. All right. So ion dipole is your first, intermolecular force. Your next one is dipole-dipole. So if we learn that ion dipole was an ion with a polar molecule, then dipole-dipole is going to be attractions within polar molecules. Okay, so we are talking a partial positive and a partial negative being attracted to each other. This is dipole-dipole forces. So, let's talk about an example. Like, let's say we have HCl. Okay. So if we have a container of HCl, remember we are talking about not the force that holds the H to the Cl. That's an intramolecular force, and of course that's a covalent force. But we're talking about what holds this HCl molecule to a second HCl molecule. So we think about this structure, and we think about bond polarity. Okay, is this a polar bond? Absolutely. Chlorine wants the electrons more, gives chlorine a partial negative, gives hydrogen a partial positive. Because this is the only bond in the molecule, the whole molecule is polar, has a bond dipole that points toward the chlorine, making not only the bond, but the whole molecule polar. So then if I were to introduce another HCl molecule, you have to think about how it would arrange itself. And of course, next to your partial negative, your partial positive would want to scoot in and be very close, because that's a huge force of attraction. So your second HCl would come in like this, okay, because this is your partial positive, and this is your partial negative, and here is this attraction between molecules, and it's a partial negative, partial positive attraction, and that is referred to as a dipole-dipole intermolecular force. Okay, so ion dipole was an ion, a full-blown ion in something polar, so something like an ionic compound that has ionized, where dipole-dipole are polar molecules being attracted to each other based on partial charges. Okay? All right. All right, so we've done two. Your third intermolecular force is called dispersion forces, or London dispersion forces, depending on what textbook you use. Some just call them dispersion. Okay, so this is your third type of intermolecular force. Okay, so we've been through ionic substances in water or other polar substances. We've been through polar substances and how they're attracted to each other. So let's talk about, what about something in Cl2, a diatomic. Okay, if you think about Cl2, it's not a polar bond, it has no partial charges. So how is this Cl2 going to be attracted to another Cl2? And you might think that it won't be, but it will. So this was in 1930 that this idea was proposed, and it was proposed by a guy named Fritz London, thus the name of London dispersion. Okay, he proposed an idea that we will refer to as an instantaneous dipole. Yes, dipole, almost spelled it wrong. Okay, and so what he said was, if you have a chlorine diatomic molecule, okay, we've already mentioned multiple times that these electrons are not stationary and they're moving. And so he posed the question of, imagine if you could take a snapshot, or you could freeze for an instant in time the electrons in chlorine. Okay, it's quite possible that at any instance in time, there's more electrons on this chlorine than there are on this chlorine. But then in another instant in time, that could be reversed, okay? So he referred to these as instantaneous dipoles, meaning if just for an instant in time, there's more electrons on this chlorine for an instant is going to acquire a partial negative, and this chlorine for an instant would acquire a partial positive. But then, of course, that could be reversed if the electrons move. And so while these aren't even truly partial charges, this unequal charge distribution creates these temporary dipoles that can then attract, it could then move your electrons. So you have another chlorine-chlorine molecule that butts up here next to the partial negative, and the electrons are going to rearrange themselves because of that temporary partial charge. Okay, so he basically said that electron movement causes temporary or instantaneous dipoles that attract other molecules. Now, as you can imagine, these dispersion forces aren't super strong, okay, because it's they're not even really partial charges, okay? They're very temporary partial charges, so they're fairly weak. Actually, they're the weakest intermolecular force we've discussed so far. Now, that being said, the more electrons something has, the bigger its dispersion forces are. And so there's a term here that we use in this section, and it is called polarizability. Kind of a mouthful. Okay, but the polarizability of a molecule is the ease in which the electrons can be distorted or moved. Okay, and the deal here is that a larger molecule with a larger molar mass is more polarizable than something that's small. Pardon my barking dog. So, if we were to compare these two molecules, okay, they're both diatomics, and so they both only have dispersion forces, but one of them is going to have stronger dispersion forces than the other, and it's the one that has more electrons, and obviously it's bromine. Okay, so because bromine is a bigger molecule, it has more electrons, which can be moved to create those instantaneous dipoles. This one, Br2, is going to have the stronger dispersion. Okay, so it has stronger intermolecular forces than the fluorine, even though technically they both only have dispersion, but it's because of the electrons. Now, one more point I want to make with dispersion, and it's a huge point, is that all molecules have dispersion. Okay, if you think about it, every molecule that exists has electrons that can be moved to create these instantaneous dipoles. So every single molecule that we'll ever talk about in terms of intermolecular forces has dispersion forces, but they're the weakest. And so sometimes they're not the intermolecular force that we mentioned because a molecule has stronger intermolecular forces. But then you have an example like these two, F2 and Br2, who don't have any other type. Think about it. They don't have dipole-dipole, they don't have ion-dipole, and they don't have hydrogen bonding, which is this last intermolecular force we're going to talk about. So in F2 and Br2, the only intermolecular force worth mentioning is dispersion.